So last week, we talked about cracks. We talked about failure and how cracks contribute to failure. And that cracks is a source of all the different kind of failures that you see in materials. Every time you see a material break is because a crack has started and has grown all the way across the material. Okay? So whenever we want to talk about fracture toughness, how strong a material is against breaking, we are talking about either preventing crack growth, getting rid of cracks, or minimizing cracks. Okay. And so we know that cracks are very, very important. How do we know whether there are cracks in a material? Because cracks is not something that you make into a material, right? It develops over time, maybe by repeated use or wind damage sometimes against a structure, cracks will develop. And you know that materials fail because of cracks, so you need to know how many cracks or if there are cracks on the surface of a material. Or inside a material. Sometimes we know that cracks can also develop inside the material. So we need to know how to detect cracks. Okay, the first way to detect cracks is through microscopy. So using a microscope. Using a microscope, it's fine. You take a piece of material, put it under a microscope, even an SEM if you want to. But that's not going to work for a bridge, right? You're not going to take a microscope and go up to a bridge and look at the span of the bridge. It's way too big, and it's not practical. So those are fine for materials where you could take a section of it and look at it under the microscope, or sometimes used for post-failure analysis. So something has already failed, you take a section of it throughout the material, and you look at the different pieces under the microscope to see if there's some development of cracks that you didn't expect. Okay, so that's microscopy. There's also X-ray. So materials will either allow X-ray to pass through or not allow X-rays to pass through. And so you can see when there are cracks inside a material. Just like, you take an X-ray to see if you have a fracture in your bone. Similar idea. And so you can take an X-ray and have it go throughout the material on site. You don't have to put a bridge inside an X-ray machine. You can use an X-ray on the field. There are instruments like that where you could take an X-ray onto the field and look at a structure to see if there are cracks within the material. But it's still really unwieldy. It's not easy to do something like that for a large structure. So another way is ultrasound. So you use sound. Ultra just means beyond the range of hearing. So you use a frequency that's beyond the range of hearing, and you can see whether the material reflects or transmits the sound. And you could detect holes or defects within the material by the way the sound is either reflected or transmitted. All right, so those are some of the ways that cracks can be detected. Okay, ductile to brittle transition. So at the beginning of the lecture where I talked about the importance of cracks, I showed you a picture of a ship that cracked in half, right? The reason why the ship cracked in half is because of the ductile to brittle transition. So the ship is made out of metal, and you would expect metal to fail in a ductile fashion. If it were to fail, something would start to bend, you would get a warning that something's not right, and be able to fix it. But that didn't happen. It just cracked in half like it was a brittle material. So people wanted to know what happened. Why did it crack in half in a brittle fashion? So in a ductile fracture, if you have a crack like this, right, because the material is able to allow for a slip or dislocation movement, the tip where most of the stress is concentrated will experience a large amount of stress at the tip. So it will start to blunt. It's going to start to pull that tip apart, and because the slip is able to deform, right? So it will eventually deform more and more, And because it's deforming, the radius of curvature, it's getting larger, so the magnified stress is getting lower, right? Remember, our magnified stress is inversely proportional to 1 over rho t. So as the radius of curvature gets larger, the magnified stress gets smaller. And so as the crack is deformed, the magnified stress on that area is actually becoming less and less. And even it could even be that it no longer is enough to create slip in this material. So ductile material is almost like it heals itself a little bit. Because it has the ability to have dislocation movement, it can reduce the amount of magnified stress and even to the level where it's no longer an issue. Okay? Brittle materials do not have that ability, and so it will crack all the way through because that crack tip stays sharp, the radius of curvature stays small, and the magnified stress stays large. Okay. So for some materials, slip does not occur under certain temperatures. Okay, and that's what happened in that ship, is that it was sitting in a cold harbor. The weather was unseasonably cold, and the temperature dipped below the temperature where slip can occur in that particular metal. They also used the wrong kind of metal. I mean, they built the ship wrong. But still, if the temperature had not dipped below that transition temperature, the material would have been able to deform ductily. Okay? So it is really important to know if your material has that cutoff, if you're going to use it in cold temperatures, and need to know what that transition temperature is, right? Okay, so why would that happen? Well, in an FCC, there is no ductile to brittle transition. So if you have an FCC, a metal that is an FCC structure, you don't have to worry about the ductile to brittle transition. And that, any guesses why that might be? So let me tell you that BCC does. Any ideas why FCC metal would not experience a ductile to brittle transition, but a BCC metal would? What do you know about the difference between an FCC and a BCC? The atomic is more closely packed. That's exactly right. So we know that FCC is a close packed structure, right? And so the more closely packed, the more slip planes there are. So remember slip planes, so it has many slip planes because of its close packed structure. Slip is when dislocation can move. Dislocation movement is the breaking and reforming of bonds, right? A dislocation moves through a structure because it's breaking one bond, reforming another bond, breaking one bond, reforming another bond. That's how slip occurs. So if you have a closed packed structure, there are lots of directions where the atoms are very close to each other. So therefore, it's easier to break a bond and immediately reform another bond because the atoms are so closely packed in. They're very close to each other. So it's easier to have slip, and you can have slip in multiple directions. BCC is not a closed packed structure. So under certain temperatures, slip becomes unavailable. Slip doesn't happen. So no slip under a certain transition temperature. That transition temperature is different materials, but BCC metals tend to have a ductile to brittle transition. Because the atoms are further apart, it is more difficult for slip to occur, and there are fewer slip planes, fewer directions where slip can occur. So any guesses on HCP, hexagonal close pack? Do you think it has a ductile to brittle transition or no? So no transition temperature. All right, so how do you test for fracture? If you want to test to see how strong a material is, you use something called impact testing. Okay? And usually, basically, you just hit it. But you have to be able to hit it in a way where you can measure something, right? So you have something like this, and you swing it into this material. So you hit it, but you measure, you control the amount of force that is hitting this piece of material. And you can even introduce cracks on purpose. You can introduce, so you might say, this is a piece of material with no cracks or very few cracks. So you etch the surface, you polish it, you make sure it's very, very smooth. And then you measure the impact testing, that's your fracture toughness, the amount of energy it takes to break this piece of material. Then you start to introduce different size cracks to this material, and then you test it again to see how much energy it takes to break, right? So that you can see the influence of cracks on this particular material. So that's something that's done very commonly in a materials testing lab. So in a material testing lab, you'll see a tensile tester. That's always there because you could get the stress strain diagram, and we know that you could get a lot of information there. You will probably get a 3-point bending test. So this is called a 3-point bending test, and you can see how much resistance to breaking there is also in that, right? You could continue to press it until it breaks. So this would be so this is impact testing, this is 3-point bending. So this is slow loading. You could control how fast you're pushing. And this is instantaneous loading. So you're hitting something, the impact is instantaneous. Okay? And that will give you different kinds of fracture toughness for your material. So the kind of test you will use depends on what kind of application your material will be under. If it will be under constant or slowly changing stress, or if it will be under sudden impact type of stress. Okay. So obviously, if you're testing, let's say, for bulletproof material, you'll use the impact testing, right? Because that's a kind of stress your material is expected to experience. Now I'm going to talk about a couple more scenarios or ways a material will break below its tensile stress. So just a reminder, this is our stress strain diagram. This is a ductile material. This is a brittle material. And for a ductile material, you have yield stress, and then also the tensile stress. There's a maximum stress there. For this, and then for a brittle material, you only have one stress, the stress at which the material is expected to break. Okay? So a couple of other scenarios where your material will break below the fracture stress or the tensile stress, or maybe will start to yield, so permanently deform below the yield stress. We need to know those things because, if you calculate a yield stress for a material and it starts to yield below that, then you need to consider that into your engineering design. The first one, it's called fatigue. Fatigue in us, humans, just means we're getting tired, right? So you can think of it the same way in a material. So fatigue happens after many, many cycles of use. So fatigue is failure. Okay, so you use the material over and over again, and eventually it breaks. A good example of that is a paper clip. I don't know if you play with paper clips sometimes, if you're bored in class, and you take a paper clip and you bend it straight, and then you bend it back again. And if you do this over and over and over, eventually the paper clip will break at the bending point, right? That's fatigue. So the first couple of times you bend it, the material is fine. It stays ductile, it doesn't change. If your fingers are very, very sensitive, you will notice that the paper clip actually becomes harder to bend. It's not enough where you will notice, but if you were very sensitive fingers, and you will start to notice that after a couple bends, the paper clip actually becomes a little more difficult to bend. Can anyone tell me why that would be? Why would the paper clip become harder to bend after a couple of times? Dislocation, moving to the bending point. So what you're doing when you bend the paper clip is that you're causing permanent deformation, right? You're deforming the material. How do materials deform permanently in a ductile material? By dislocation movement. Right? So dislocation, there must be, you're creating or moving dislocations within the paper clip part that's bending. Okay, so that's how it's bending. You're creating dislocation movement, slip, okay, in that area. You're creating more and more dislocations in there as you bend it more and more. That's also called cold working, right? You're creating more dislocations. Those dislocations eventually interfere with one another, so it becomes more difficult for slip to occur. That's why when we looked at that video of the man who created the Woods steel, and he would take the metal out of the furnace and then he would either hit it with iron or use something to stamp on it, right? Like to hit it. So he's using dislocation, he's creating dislocations and defects by deforming the material. So that's called cold working. And so as you bend the paper clip, you're cold working the paper clip, creating more and more dislocations in that bending area. Eventually, it will experience fatigue, and this is what will happen. You will get crack initiation. Okay, even if there were no cracks on the surface before, you get enough dislocations that bunch together, you're going to get a crack. Okay, so you get crack initiation. And then you get crack growth as you continue to bend it, and then eventually it fails. So you can actually test this in the lab, and people do. This is another common test in a material testing lab, is stress versus a number of cycles. So this is called the SN curve, because it's stress versus a number of cycles to failure. So basically, this is a machine that takes the material and just applies stress to the material, either in a bending mode, compression, tensile, whatever it is. Okay, and they just apply stress over and over and over and see when the material breaks. So some materials will just, so as you increase the stress, the number of cycles becomes lower to breaking, right? As you reduce the stress, you can continue to use the material for a longer period of time. So that's a typical SN curve. There are some materials that will have what is called a fatigue limit. So for some materials, if you use the material at a low enough stress, you don't have to worry about fatigue, because you can use it for as many cycles as you want and it will not break. So for some materials where the stresses are low enough, the buildup of damage, dislocations will not lead to failure. It is able to compensate for the damage. For other materials, it will not. The damage will accumulate, and then eventually it will break under enough cycles. And so this is something you could test in the lab, but also remember, if you have a surface defect, it will also make fatigue happen faster. Right? Because if your fatigue happens because you get crack initiation, you get a crack, then it starts to grow and then it fails. So if you already have a crack on the surface, then fatigue will happen much more quickly. So if you were testing a material, it's also important to know if you have any cracks on the surface, and then also how does that affect your SN curve. And you need to take that into account when you're actually using a material in the field. Can anyone think of an application where materials will experience fatigue? What is something that's used where the material experiences repeated cycling of stress? What is it? Spring, yes. Thank you. So a spring, right? It stretches and compresses over and over and over. Your shock absorber in the car, the springs in the car. Fatigue is very common. Okay? Airplane wings. I know it doesn't look like the airplane wings move. The airplane doesn't flap its wings to fly, right? But if you ever see an airplane take off, the wings actually vibrate quite a lot. Okay? It vibrates this way. And so that joint between the wing and the fuselage will experience fatigue. So that's very important, right, when you fly, to make sure that fatigue is not an issue in the airplane wings. If you see this, and let's say you know that you are going, let's say this is your airplane wing material, and you know that the airplane wing may fail at a stress of, let's say, this. So this is the maximum number of cycles you should allow your airplane wing to fly, right? So if this is 1,000 cycles, then you know your airplane wing probably should fly 500 cycles before you change your airplane. Sorry, not fly, but vibrate. So obviously it's going to be a lot more than 1,000 because the vibration is going to be, millions of times on any given flight. So you need to know if your airplane wing is made out of a material that doesn't have a fatigue limit. You need to know at what stresses the wing is going to experience and how many times that you're going to allow it to be used. Okay, so that's why this is important to know. Anything that experiences vibrations will undergo fatigue, right? Vibration is just repeated cycling of something. Your chair, the seat that you're sitting on, it's repeated cycling, right? You sit on it, you get up, somebody else comes on it, sit on it, gets up. So that's a repeated cycling of stress. So fatigue is very, very common in material usage, and that's why it needs to be taken into account. One way you can reduce or slow down fatigue is increase surface hardness. Most of the times when fatigue, repeated cycling happens, the crack initiation happens on the surface. And so if you can make the surface harder or more difficult for cracks to initiate and more difficult for cracks to grow, then your material will be more fatigue resistant. So one way, it's called shot peening. Shot peening is just taking little pellets and hitting the surface of your material with it. So it might seem counterintuitive, like you're deforming the surface of your material by hitting it with stuff, but you're forming little rounded indentations on the surface. So you get little rounded indentations on the surface with the shot peening. What this does is that it makes that surface harder. So it's basically cold working. You're cold working the material by inducing small indentations, but they're not sharp cracks. So shot peening is a very common and cheap way to harden the surface of any material, and that can slow down fatigue. Another way is called case hardening, and this is through a diffusion process. You diffuse impurities into the surface layer of your material. Usually it's carbon, nitrogen, a small atom that's common, easily found, and easily diffused into materials. Okay, so you diffuse impurities into maybe like the first couple millimeters, very, very small. But because their impurities also slow down or prevent slip, and that makes the surface harder, makes it more difficult for cracks to grow, and increases fatigue resistance. Another way, or another similar or related way where a material can fatigue is due to temperature changes. So let's say you have a material that there's no stress on it, but undergoes temperature changes, large temperature changes, hot, cold, hot, cold. The material will expand, contract, expand, contract. If it's doing this, then it's like fatigue, it's like having a stress on it, and so it could experience fatigue. So thermal cycling can also create fatigue. And then other ways where materials can fail is, an example of that is corrosion, right? You chemically alter the surface And that chemical alteration can end up creating cracks and causing the material to fail. And then the last one for failure is creep. Creep is when you have failure at lower stress due to constant stress. So you're using something at constant stress. So this is not cycling, it's not fatigue, constant stress. But you're using the material at elevated temperatures. So the temperature is high, you have constant stress, and you could get something that experiences creep. You could kind of imagine if you have, let's say, a spring that's loaded. So you have a spring with a weight, but you're not cycling that. The weight is just hanging on the spring. And you heat this up. You can imagine that the spring will start to stretch and stretch and stretch and stretch. And if it's hot enough, maybe it will even break. Can you think of a material application where that happens in creep? What is something that you would use that you would have to worry about creep? What kind of application? This one's a little harder. Fatigue is really common. So turbine blades. It's a most common example used when people talk about creep. A turbine blade, right, in a jet engine or whatever, you have blades. Okay, it's going to look like a flower. But anyway, it's a blade. It's spinning and it's inside some sort of engine, and it's hot. Turbine blades uses hot air, right? It's hot air that's flowing through. So it's very, very hot. And it's spinning, so it has centrifugal force. So the blades feel a force this way constantly when it's working. So it's a constant stress pulling out, and it's under high temperature. And turbine blades work only if the turbine blades are very, very well fitted to the outer layer, right? It can't have too much of a gap. So if there is creep, that means the material starts to elongate. It will hit this outside, and the entire turbine will experience catastrophic failure. Okay, so it's really, really important when looking at turbines to make sure that the material does not experience creep, because any elongation in that turbine blade will cause the entire thing to fail. And so when you look at creep, you look at elongation or strain versus time. Okay, so this is elongation or strain due to creep and time, and you're going to see something behavior that looks something like this. It will go through 3 stages. Stage 1 is called primary creep, and some of the elongation is just due to the bond stretching. You apply stress to any material, you're going to get elastic deformation, right? So that you can't prevent that at any temperature. There's going to be some bond stretching, so there will be some strain. But the strain you'll see is starting to decrease with time. The growth of that strain is decreasing with time. And that's because there's some amount of hardening happening, right? As you get bond stretching, and then you get dislocation movement. And as you start to increase the number of dislocations, it starts to work harden. And so it becomes more and more difficult to string. So that's primary. So you get bond stretching, dislocation movement or slip, work hardening. That all happens in the first stage. The second stage, strain increase is constant. So you see this, the slope is kind of constant here. It's not changing. And that's because there's a balance between slip and recovery. So when we talked about metals, and we talked about creating dislocation movement, slip, all of those things, we also talked about how to get rid of the damage, right? We said that we could anneal the metal. So if we take the metal up to higher temperatures, you get some of that effects of strain going away. You get recovery, recrystallization, and grain growth during annealing. Creep is something that happens at high temperatures. And so at high temperatures, you're going to get some annealing effects. So during this stage, you're creating dislocations, but also the recovery is happening. And so they balance each other out. It doesn't get harder, but it doesn't get softer. It kind of just continues to grow in a constant manner. Then you get to stage 3, and that's basically crack growth and failure. So at some point, recovery can't keep up with the dislocation growth, and the material will just fail. So experience an increase in strain, and then the material fails. So if I show you, this is time, strain due to creep. If I show you this diagram, and I tell you all 3 lines are from the same material. I have one material, and I could get these 3 different behaviors for creep. What might be the difference? Why would they be so different? Very good, different temperatures. So at very low temperatures, maybe you never get failure, right? The temperature is low enough where at constant stress, it's not going to have enough buildup in dislocations to do anything. So you can use that at that temperature, at that stress indefinitely. It doesn't break. And then if you raise the temperature, it might experience creep. And then if you raise the temperature some more, it'll experience creep faster, right? It starts to fail at an earlier point in time than here. I should draw this a little. So why do creep happen? It's actually quite complicated. It is increase in dislocations. It will have eventually cracks that form, propagate. But in every material creep, the dislocation increase happens a little bit differently. So it really is not something that can be easily predicted. You basically have to do experiments. You take a material, put it under a load, and then at an elevated temperature to see how long it will take for that material to have significant strain. And so sometimes it might take too long. Like let's say you're going to use this material at an elevated temperature for 10 years. You're not going to test your strain for 10 years before you say whether this material can be used, right? So in those cases, they would increase the temperature. They would say, let's try to heat it at 10 times the temperature and then guess backwards at what point the material will fail at a lower temperature. So they try to speed up the experimental process. It's not perfect, but sort of what the engineers have to do. I think I'll stop here to give you some time for those of you who haven't picked up your midterm yet. And then I'll finish off, actually, I think this is pretty much all the information I wanted to talk about in terms of failure. I added another article into E3 under supplemental reading, and it is about a ceramic material that can be deformed. And it just was published, I think in October, this last month in Science. And they can actually see a 20% strain on a ceramic material. Okay, and so if you're interested in that, I thought it was fascinating. You could read it, and then we could talk about it a little bit next week.